Lenz's law is one of the most highly regarded physics ideas. This law became heavily present when this week's challenge surfaced. Use a magnet or electromagnetic-based system to demonstrate and measure magnetic damping. The simplest experiment was undertaken, taking inspiration from both Lenz's law and experiments that were undertaken throughout high school physics lessons. A rare earth magnet is released and allowed to fall down the middle of 3 differing types of piping, being copper, aluminium, and a clear thermoset plastic. The piping was held up by a retort stand and a Boss head clamp. The copper and aluminium tubes were both identical in size, being 50 centimeters long, with a radius of 1.2 centimeters. The plastic tube alternatively was longer and had a larger radius of 1.5 centimeters. Although the radius may have impacted results if the metal radiuses differed, since Lenz's law is not present within the plastic tube, this problem is not impacting. Along with this, the plastic tube was larger than 50 centimeters in length. To solve this problem, a measurement line of 50 centimeters was drawn onto the tube to ensure a consistent starting point. To ensure each experiment was done with the same conditions, apart from the variable tube material, the magnet that would fall down the center of the tubes were held at the top of each material via a weaker magnet and placed at the same height, which was measured by the height of a 50-gram weight. This meant that the magnets could start exactly at the 50 centimeter point, with the magnet being held at the 50 centimeter line within the clear tube, whilst also keeping a constant start speed and force in all trials. The copper tube had the highest conductivity, and looking at Lenz's law, which states the direction of an induced current is always such as to oppose the change in the circuit or the magnetic field that produces it, it is shown that there would be a larger force at play in the copper than either the aluminium or plastic tubes. To travel the 50 centimeters, the magnet took an average of 4.43 seconds. This leads the magnet of mass 10.6 grams to be falling approximately at 0.23 meters per second when it leaves the tube. The aluminium tube took an average of 4.39 seconds, falling at a faster rate than the previous copper trials at a rate of 0.24 meters per second. Since the magnet simply fell through the clear plastic tube, it finished in a faster average of 0.49 seconds and a leaving velocity of approximately 4.17 meters per second. After all the trials were completed, the experiment was then repeated using 2 magnets, comparing if the order of speeds are equal to that of the single magnet experiment. The results corroborated with the single magnet results. A magnet sensor was also placed in front of each material to allow observers to see the magnet pass through the tube. When the magnet falls down the pipe, the metal attracts the falling magnet. The changing nature of the moving magnetic field in the electrically conductive environment creates a resistance which applies negative force on the magnet and therefore slows it down. The main non-ideal results related to either the movement of the tube when releasing the magnet or a human error when recording the stopwatch times. These values were dampened by completing experiments 3 times to ensure accurate results could be determined for a valid experiment. Ultimately, the demonstration of Lenz's law through letting a magnet fall through a metallic tube is enough to demonstrate and give you the ability to measure the magnetic dampening of the system.